We talked last time generally about the concept of work and how work is defined. I would like to make a distinction now between reversible work and irreversible work. Imagine, for this purpose, imagine the following experiment. Imagine, say, a gas enclosed inside a cylinder. In here is a gas, let's say, and this cylinder has volume V1. And there's a movable piston indicated here that you can use to compress or expand the gas from the outside. So you can move this piston and change the volume of the gas. I drew deliberately thick walls of the cylinder and also of the thick wall for the piston to indicate that this gas is thermally insulated. So there's no coupling to the outside, and that there's no possibility for energy to flow in the form of heat. This is our movable piston, and this we can use to compress the gas, and this, in order to do that, we have to perform work on the gas. Of course, there's also no possibility for the gas to exchange particles with the outside world, so the walls around the cylinder not only impede heat flow, but they also impede exchange of particles. And so the number of particles is strictly conserved. Now you can move the piston, say you want to compress the gas, and you can move the piston either slowly or you can move it fast. And let's consider what difference that makes, whether you move the piston slowly or fast. So let's say you have, in a certain time interval, delta t, you can either move the piston slowly or you can move it fast. If you move it slowly, then let's say this is the original volume of the gas, and then you move it just a little bit in this short period of time. So you move it a rather small distance, and the gas is now contained in a smaller volume V2. And still you have the thermal insulation around it. So there's no energy was exchanged in the form of heat, only work was performed on the system. When you do this sufficiently slowly, then you can assume that at all times the gas is in thermal equilibrium. You can, if you like, decompose the movement into very small steps. You compress the gas just a little, tiny little bit. The volume is just a little bit smaller, and then you pause, and the gas is still in equilibrium. So meaning that its macroscopic properties, its macrostate, is still characterized by the typical macroscopic data, volume, particle number, and energy, and nothing else. And that fully characterizes the macroscopic state. Then you move another little bit and pause, and again the system is in equilibrium. So at all times, when you do it sufficiently slowly, you can say the gas is in equilibrium. What does this mean for the entropy of the gas? Now let me indicate a little picture schematically, we have state space, or we have the space of all states of the gas. And let me indicate with these curved lines of constant entropy. And entropy increases in this direction. Now, initially, we have a system with fixed particle number, so the particle number is given as macroscopic, as part of the macroscopic data. We have a fixed volume. Initially, it's the volume V1, so fixed volume. And let's say we have the energy given as an expectation value. Then we should use the canonical ensemble. And the initial state, macrostate of the system, is a canonical state corresponding to a certain initial internal energy. Let me indicate with this horizontal line all states that have the initial internal energy. The internal energy is the expectation value of the Hamiltonian. And the Hamiltonian has a dependence on a control parameter volume. So you can model the enclosure inside the cylinder as the enclosure inside a potential with infinitely steep walls, where the walls of the cylinder are. So the Hamiltonian contains a potential well, and the potential well, the shape of the potential well is parameterized by the volume, and initially we have the volume V1. Now initially the system is in equilibrium, so initially it is in that state which, given this internal energy, maximizes the entropy. And this is this unique state here. This is the initial state, and this is a canonical state with internal energy U equal to this expectation value of the Hamiltonian at volume V1. What happens now if we compress the gas slowly? We learned last time that this is a driven Hamiltonian evolution. So we have we change from the outside, we change the volume. Now the volume is a parameter, a control parameter of the Hamiltonian. So effectively we have a time-dependent Hamiltonian when we compress. And under this time-dependent Hamiltonian, the state evolves with unitary evolution. Unitary evolution preserves the entropy. So after this compression, the system is in a state which has the same entropy as the initial state. So in this schematic picture, we are moving along this curved gray line, which is a line of constant entropy. So compression implies that we are moving along this gray line of constant entropy. This is a driven unitary evolution. And then we end up in this state here. If we assume that the compression is sufficiently slow, then we said at all times the system is effectively in equilibrium. So when it's sufficiently slow, then we can be certain that this final state is also an equilibrium state and hence is also a canonical state. Canonical state is characterized by the expectation value of the internal energy, and now after compression we have a new Hamiltonian because we changed the volume, and the volume is a control parameter of the Hamiltonian. So we have a new Hamiltonian h of V2 of the new volume. And the final state is characterized by the expectation value of that new Hamiltonian. Let me indicate by the green line the set of all states that have a given expectation value of the Hamiltonian at the new volume V2. Now the final state, the red dot on the right, the final state has a higher internal energy than the initial state because we performed work on the system. And this work that we performed on the system led to an increase of the internal energy of that system. So the expectation value of the Hamiltonian in the final state is higher than the expectation value of the Hamiltonian in the initial state, and the difference between the two is just the work that we put into the system. And let me indicate this symbolically here by saying this is delta work. So by going from the blue horizontal line to the green line, we added work delta W. Okay, so the final state is now on this green line. It has this new internal energy, which is higher by an amount delta W. And it's also canonical, because we said when we compress slowly, the final state is in equilibrium. So it must also be, just like the initial state, it must be on the green line, the state with the highest entropy. And therefore, in this picture, the green line is the tangent to this curve at the final state. Yes, that's how maximum entropy states are characterized. So the final state here is also canonical, now with internal energy given by the expectation value of the Hamiltonian at V2, expectation value in the final state. So what have we done in this slow scenario? We have performed work on the system, we've increased the internal energy of the system, but without changing its entropy. The final state is still on the same entropy curve and therefore has the same entropy as the initial state. So the change of entropy due to work performed on the system is equal to 0. For this reason, this work that we performed on the system is called reversible work. It's reversible because it didn't lead to an increase of entropy. And work is reversible as long as we perform it sufficiently slowly. But what happens now if we perform the work fast, if we compress the gas inside the cylinder fast? Then in this symbolic picture, if initially we had this volume, then in the same time interval, we move the piston by this much greater distance and compress the gas now to a volume Vt primed, which is smaller than V2 primed, which is smaller than V2, much smaller. Now you all know from experience what happens if you compress a gas very fast. Then for a while you push the gas out of equilibrium. You create shock waves which only after some time then dissipate and vanish, and you are back to equilibrium. And then the gas then re-equilibrates. But initially, after this very fast movement of your piston, you generally have shock waves. These shock waves lead to inhomogeneities of the gas. And so it's no longer in equilibrium. Yeah? So it's out of equilibrium. And then only after some while the gas settles in equilibrium again. Let's see what this means in our picture in state space. We have the same initial situation with the initial canonical state before compression. Then we compress the gas rapidly. This doesn't change the fact that this is driven unitary evolution. You have compression means you vary this external control parameter. You have effectively a time-dependent Hamiltonian. And for the rest, you have an isolated system. There's thermal insulation, no particle exchange. You have an isolated system. So under a time-dependent Hamiltonian, an isolated system still evolves unitarily. So the state still moves along this gray curve of constant entropy, as before. Let's say it moves a lot further away because you compress much more than before, and it moves to this state here. The difference is, to the first scenario, the difference is that this is now no longer an equilibrium state. What happens next? The shock waves or the inhomogeneities that you create by this rapid compression, they fade away and the gas settles in equilibrium. So after this, you don't move the piston anymore. The system is completely isolated and also not driven anymore. So its internal energy must stay constant and it settles in equilibrium. Let's say this state that you created by moving the piston very fast has a certain internal energy. It's the expectation value of the Hamiltonian at this new volume V2 primed. This is higher than the initial internal energy because you supplied work, you performed work on the system. So you added to your initial energy, you added some work, delta W, let me call it prime for this second scenario. So you have a higher energy, but you recognize that now this state, which is not canonical, it's amongst all states on with the same internal energy. So all states on this green straight line, it's not the one with maximum entropy. That's precisely what indicates the fact that it's not an equilibrium state. When the system settles then in equilibrium with the same internal energy, this means that in a second step, the system moves on this green line because it must maintain the same internal energy towards the state with maximum entropy. And this is, say, the state here. So this is the subsequent relaxation towards an equilibrium state. Now this is the final state, which is again canonical, and it has the same energy as this intermediate state, but it has a higher entropy. Yeah, so here you have three states. You start with state number 1, then you have state number 2, and then you have a subsequent relaxation towards state number 3. Going from 1 to 2, you don't change the entropy, but going from 2 to 3, this relaxation increases the entropy. So the net effect is that in this fast scenario, the change of entropy due to the work that you performed is now positive, is strictly larger than 0. And this is called irreversible work. It's irreversible because it leads to an increase of entropy, a change of entropy that's strictly larger than zero. And this happens when you perform work too fast. Now, in thermodynamics, one generally assumes that one is in the limit of reversible work. So in thermodynamics, one generally assumes that all work that is performed on systems is performed sufficiently slowly such that work can be considered reversible. It's not easy to quantify how slow, sufficiently slow means. The system on which you perform work generally has a typical time scale on which it relaxes towards equilibrium if it's disturbed, and if it's driven out of equilibrium. It typically relaxes back to equilibrium on a typical time scale, relaxation time scale. If the work and the variation of the control parameter is done on a time scale much longer than this relaxation time scale of the system, then to a very good approximation you can assume that at all times during the process the system is in equilibrium, and you can assume that work is done reversibly. And that's what we are going to assume when we look at typical thermodynamic processes. And the fast scenario, that occurs only if the work that you perform and the variation of the control parameter happens on a time scale shorter than this typical relaxation time scale. And then so the system is driven out of equilibrium. It doesn't have time to re-equilibrate during all intermediate steps of your process. So the time scale on which you perform work is shorter than this relaxation time scale, and only at the end of the process the system has to relax back to equilibrium, and this leads to the irreversibility and an increase of entropy just due to work. This limit that one assumes often in thermodynamics, that work is reversible, is called the quasi-stationary limit. The quasi-stationary limit means that processes are sufficiently slow, so they happen on time scales much longer than the relaxation time of the system, so that at all times during the process the system can be considered to be in equilibrium. Remember the definition of equilibrium. Equilibrium means that at all times the system can be described by a Gibbs state, so of the form e to the minus some Lagrange parameter ai, where in the canonical case you have beta times Hamiltonian, but more generally you might have other macroscopic observables and associated Lagrange parameters. So you're assuming that this description with a Gibbs state with the appropriate observables and Lagrange parameters, that this is possible at all times during your process. And what we saw is that in this limit, work is always reversible. So, changes of entropy due to work are zero. There are no changes of entropy due to work. Let's look at the change of internal energy of the system. So this is the difference of internal energy. Very generally, regardless of whether the process is reversible or not, whether we are in the quasi-static limit or not, what's always true is that the change in internal energy is due to supply of heat and supply of work. This is always true. Now, if we assume that the system is initially in equilibrium and at the end is also in equilibrium, so we say, we look at the difference of internal energy, assuming that both the initial and final states are canonical. Now, here for simplicity I limit myself to the canonical case, and final meaning after the system has relaxed. So this still includes the fast scenario, where the system is temporarily driven out of equilibrium, but then it relaxes, and after relaxation, the final state is again an equilibrium state, so a canonical state. So if I look at the difference of internal energies of the initial and final states, then we also know that this must be equal to TdS minus PdV. This follows from our very general framework of statistical mechanics. In all of this, we are assuming that the particle number is conserved. So we are not considering processes involving an exchange of particles. We're just looking at processes that may involve an exchange of heat and or work. Think of now the process that we were looking at on the previous page, the compression of the gas with a piston. The system was thermally insulated, so there was no exchange of heat, only work supplied to the system. So in our piston example, the insulated piston, the supply of heat was equal to 0. The change of entropy, ds, we learned that this was equal to 0 if the process was quasi-static. So if we performed the work in a reversible manner, if we performed the work slowly, the process was quasi-static, and then there was no change of entropy. There's no increase of entropy. So this is 0 if the process is quasi-static. But the change of entropy is larger than 0 otherwise. From this we conclude, well, on the left-hand side of the equation, then you just have delta W's, the work performed. And on the right-hand side, if the system is, if the process is quasi-static, the first term vanishes and you just have minus PdV. So you find that the work is equal to minus PdV if the process is quasi-static. Or in other words, if the work is reversible. If the process is not quasi-static, in our example, when you compress the piston very fast, the work that you perform is irreversible. The change of entropy is larger than 0. Then on the left-hand side, you still have delta W, so the amount of work. On the right-hand side, you have TdS, where ds is larger than 0. The temperature is also larger than 0. So TdS is larger than 0. So you have delta, the work performed, is equal to something which is larger than 0 minus PdV. Therefore, the work is larger than minus PdV. So this is an important result, that the equation that sort of for infinitesimal work, this is minus PdV only if the process is quasi-static, if you perform the work sufficiently slowly in a reversible manner. Only then is work equal to minus PdV. Otherwise, the work is larger than that. And this means in the example of our piston, if you want to compress the piston, the gas, from some initial volume to a smaller volume, you can do this either slowly or fast. If you do it fast, then you have to, it's less efficient because you have to perform more work to arrive at the same final volume. One final consequence. Let's now generalize the situation and let's allow for processes where also an exchange of heat is involved. When you allow for the exchange of heat, then just as in the case of work, you have to make a distinction between quasi-static processes and other processes. In the quasi-static case, I mean, this equality up there still holds, delta Q plus delta W. That must be equal to TdS minus PdV. In the quasi-static case, delta W equals minus PdV, and hence the amount of heat exchange, delta Q, must equal TdS. So this is true in the quasi-static case. If the process is not quasi-static, then the amount of work performed is larger than minus PdV, since the sum of heat and work must still give the same change of internal energy. And so the du here on the left-hand side, this is fixed. In the case where the process is not quasi-static, the amount of work is larger than minus PdV. Now, in order to ensure that the sum of work and heat is still the same change of internal energy, the amount of heat must be smaller than TdS. So delta Q must be smaller than TdS for processes that are not quasi-static, that involve irreversible work. So here you see that the familiar expressions that occasionally we've already worked with for heat and work, namely minus PdV, and for mechanical work, we also had magnetic work and other kinds of work, but for mechanical work it's minus PdV. And the expression for heat, TdS, they hold only in this quasi-static limit. And when we now, in the following, look at thermodynamic processes, we will always assume that we are in the quasi-static limit. I'd like to illustrate with a specific example that work and heat depend on the process, are not properties of initial and final states of the process, but do depend on the path that you take when you go from one state to the other. And I would like to illustrate that in the case of a perfect classical gas, satisfying the ideal gas equation, pressure times volume is equal to nKT, and throughout the process we will keep the particle number fixed. And let's use immediately the new concept that we have introduced. Let's assume that the process is quasi-static. What is the process that we are looking at? I draw here a diagram with the volume on the horizontal axis and the pressure on the vertical axis, I have an initial state characterized by two thermodynamic variables, pressure and volume, P1 and V1. And I have a final state characterized by P2 and V2. And of course particle number, but I don't write this explicitly because the particle number doesn't vary in the course of the process. N is fixed throughout. And now let's consider two different processes, both leading from state 1 to state 2, but on different paths. Let's consider the first process, A, going along this path. And we have an alternative process going this way. This is process B. Let's now consider the work, the mechanical work received by the system in the course of either process. Since the process is quasi-static, we can use the formula for the infinitesimal work when we change the volume by an infinitesimal dV. That's minus P dV, because we are assuming that this is quasi-static. When we want to know the total work received by the system, performed by us and received by the system, then we have to integrate this infinitesimal work over the entire path. When we go along the path A, this is decomposed into two steps. First we go up this vertical line, we go up this vertical line, and then there's this corner, and we go horizontally. The first section, when we go up vertically, this step happens at constant volume. So the volume doesn't change at all, and hence there's no work involved. And on the second piece, going from left to right, the volume increases from V1 to V2 at constant pressure P2. So the infinitesimal expression for the work is easily integrated. The total amount of work is simply equal to minus P2 times the difference V2 minus V1. Since the pressure is constant along this section of the path, it's P2 everywhere, then we just have to integrate over dV from the initial to the final state, and this simply gives the difference of final and initial volume. If, on the other hand, we go along the path B, then we go horizontally parallel to the v-axis first, and afterwards we move up vertically. So here we perform work in the first half of our process. When we go horizontally, we change the volume from V1 to V2, and this happens at constant pressure P1. So the expression minus P dV is again easily integrated because the P is constant, it's P1, and the integral over dV is again the difference of the volumes. So we have minus P1 times the difference of the volumes. And then when we go up vertically, this happens at constant volume V2, so the volume doesn't change anymore and there's no mechanical work involved. So that's it. This is the work performed along path B. And you see that these two expressions are not equal because the two pressures P1 and P2 are not equal. And hence, indeed, the work differs for the two different paths. Likewise, we can look at the heat received. Now, the infinitesimal expression for that is TdS, but which we can also write as du, the change of internal energy, minus the infinitesimal work. If we assume a monatomic gas, a monatomic ideal classical gas, then the formula for the internal energy is 3/2 nkt, which is the same as 3/2 pressure times volume. And then we can say the heat received along path A, that's the change of internal energy between initial and final state. So it's U2 minus U1, it's the change of internal energy, minus the work received. Heat received plus work received must, of course, give the change in internal energy. And here we solve for the heat received. For the internal energy, we can use the formula 3/2 PV. And for the work received along path A, we can use the previous result. You combine that, you find that the heat received is 5/2 P2 V2 minus 3/2 P1 plus P2 times volume V1. And likewise, you can find a formula for the heat received along path B. And again, these are obviously not equal. So you see in this specific example, heat and work received do depend on the path that I take when I go from one state to the other. After these sort of preliminary remarks about heat and work and processes, I'd like to say a few words in general about the scope of classical thermodynamics. The general setup is that you have multiple systems. Say you have a system A, you have a system B, you may have another system C, and so on. You have several systems. These systems can exchange energy in the form of heat, work, particles. So here you might have exchanges of heat, particles, work, and so on. Now mainly those three. You can have barriers between systems. You can have here, for example, the systems A and B. They are separated by a barrier or a wall. Such barriers or walls, they impede the exchange of all these resources, so heat, particles, and so on. And you can do this selectively. So you can, for example, you can, between two systems, you can insert a wall that impedes the exchange of particles, but it's a perfect heat conductor, and therefore it allows the exchange of heat between A and B. Alternatively, you can have a wall that impedes the exchange of particles, but is also insulating, so it also impedes the exchange of heat between the two systems. You could have a wall or a barrier that is movable. It's like a piston. So the barrier can move in space. This allows for one system to perform work on the other. So this allows for exchange of energy in the form of work, but it impedes the exchange of particles. And then depending on whether or not it's thermally insulating, it can allow or impede the exchange of heat between the systems. So you can construct between the various systems in your collection, you can construct different kinds of walls, and you can select which kind of resources the systems are allowed to exchange and which not. Then you can also have so-called reservoirs or sources. This is a reservoir or a source. This can be, for example, a heat bath, or sometimes also called a ThermoStat. This is a system which is so large, very large compared to the systems of interest that interact with each other, that any exchange of heat with this heat bath doesn't change its temperature. So let's assume that I have here in this lecture room, I have a huge block of ice, and that maintains temperature 0 centigrade. And when I put a small system in contact with this huge block of ice, then through the exchange of heat, my small system will eventually acquire temperature equal to 0, but the temperature of the block of ice will not change. So it's a system that is so huge that its temperature can be considered fixed. And any smaller system that I bring in contact with my heat bath will acquire this temperature. Yeah? So such a heat bath or thermostat fixes the temperature. Now, when I bring a heat bath in contact with system C, then what I do is I ensure that system C has temperature T. I fix the temperature of system C. There are also other kinds of reservoirs. There are so-called volume reservoirs. A volume reservoir fixes the pressure. So the volume reservoir is connected to system C by a movable barrier, and the reservoir has a fixed pressure and ensures that the system C will have the same pressure. Yeah? And the interaction between the two systems will establish an equilibrium. Equilibrium is characterized by equal values for the intensive variables. Pressure is one such variable, and so the system C will acquire the same pressure as the volume reservoir. Then there are particle sources. So you could also have a particle source, and such a particle source fixes the chemical potential. Yeah? So reservoirs quite generally fix values of intensive variables. Whereas barriers or walls, they impede the exchange of extensive quantities. So if they impede the exchange of particles, N, they impede the exchange of energy, either in the form of heat or in the form of work. So, for example, if this is a rigid barrier that cannot move in space, it fixes the volume and it impedes the exchange of work. Now, this is sort of very schematically the general setup. So you have multiple systems exchanging selectively and partially impeded by barriers. They exchange selectively heat, work, particles, and then this whole setting is in contact with reservoirs that fix intensive variables. One very typical example for such a setup is a thermal engine. And this is sort of, traditionally sort of a main focus of thermodynamics, that you look at such engines of different kind, and you will also, on the problems that's forthcoming this week, you will also have a look in a lot more detail at one specific example of a thermal engine. A very generic setup is that you have a system that may be a gas or liquid. More generally, it's called the work medium, whatever it is. This work medium performs work. So I have an engine and I would like to extract work from the engine. What does the engine do? It converts heat into work. For the engine to be able to do that, it must be in contact with a heat bath, a hot reservoir at temperature T hot, at a high temperature. From this reservoir, the work medium extracts heat, Q hot. But the work medium is also in contact with a second heat bath at a lower temperature, T cold. And to this, it exchanges heat also with this cold reservoir. Heat flows from the work medium to the cold reservoir, and the amount of heat exchanged here is Q cold. Now, for this whole process, we must, of course, have energy conservation. First law of thermodynamics and energy conservation. So when we look at the energy balance, the work that the work medium performs, W, must equal the net amount of heat received by the work medium, and that is the work received from the hot reservoir minus the heat given away to the cold reservoir. Both the hot and the cold reservoir are in equilibrium at all times. When heat flows from the hot reservoir to the work medium, the internal energy of the hot reservoir is decreased by this QH. This decrease of internal energy corresponds to a decrease of the entropy of the hot reservoir. So there's a decrease of entropy of the hot reservoir, delta entropy of the hot reservoir. Now the relationship holds for change between change of internal energy and change of entropy. du is equal to TdS. That holds for the hot reservoir. Now, since the QH is the heat given to the work medium, so the QH is minus the change of the internal energy of the reservoir. We have a minus sign here, and we have in front the temperature of the hot reservoir. So it's minus the temperature of the hot reservoir times delta entropy of the head reservoir. And likewise for the cold reservoir, the heat flowing towards the cold reservoir increases its energy, its internal energy, by QC. And this corresponds to an entropy increase of the cold reservoir, delta S cold, and the relationship is by a factor T cold. Let's now look at the entropy balance. Now, such a thermal engine typically works in cycles. So it extracts heat from the hot reservoir, it performs work, it gives away heat to the cold reservoir, and then after a certain cycle, the work medium is back to its initial state. And now we look at the situation after a full cycle. So the work medium is back to its initial state. And then, of course, the work medium is in exactly the same macro state with exactly the same internal energy and also exactly the same entropy. So after a full cycle, the change of entropy of the work medium is equal to 0. As for the changes of the entropies of the two reservoirs, the second law says that if this process is reproducible, and it is, in such a reproducible process, the total entropy can only increase. So the total entropy, which is equal to, or the change of total entropy, which is equal to change of entropy of the work medium plus change of entropy of the hot reservoir plus change of entropy of the cold reservoir, this can only increase, so this must be larger or equal to 0. Now, since the change of entropy of the work medium is equal to 0, this implies that this must be larger or equal to 0. Now, we can use the equations that we have for the amounts of heat flowing from or to the hot and the cold reservoir and solve these equations for delta entropy of the hot reservoir and delta entropy of the cold reservoir. And then this condition, that delta S hot plus delta S cold must be larger or equal to 0, translates into amount of heat flowing to the cold reservoir divided by temperature of the cold reservoir must be larger or equal to amount of heat received from the hot reservoir divided by temperature of the hot reservoir. Or in other words, Q cold over Q hot is larger or equal to T cold over T hot. Now we can introduce a parameter called, for the efficiency of the process of the thermal engine. The efficiency of an engine, eta, that is the fraction of the heat received from the hot reservoir that the engine converts into useful work, into work W. So it's the fraction of the work done by the engine over the heat received from the hot reservoir. By energy conservation, by this equation up here, we can express the work as the difference of the two heat fluxes, and we find that this is equal to 1 minus Q cold over Q hot. And this ratio, for this ratio in turn, we can say this ratio is larger or equal to T cold, the cold temperature over the hot temperature. So 1 minus that ratio must be less or equal 1 minus the cold temperature over the hot temperature. And this means unless the cold reservoir is at absolute zero temperature, which in practice you can never achieve, this efficiency is strictly smaller than 1. So it is impossible, by the second law of thermodynamics, it's impossible, no matter how the engine is constructed in detail, just by the second law, it's impossible to construct a machine, an engine, that perfectly converts to 100% heat received from a hot reservoir into useful mechanical work. There will always be a fraction of this work received that the engine will have to give away to a cold reservoir where it is lost, where it cannot be used and transformed into mechanical work. And the traditional formulation of this finding is that there is no perpetuum mobile of the second kind. Perpetuum mobile of the first kind is an engine that violates energy conservation, that basically creates energy out of nothing. This is obvious that this is not possible. And a perpetuum mobile of the second kind would be an engine that perfectly converts heat into work, and this is not possible either by the second law of thermodynamics.